to a mini-series of videos at Higher Mathematics on exponentials and logarithms. And in this first video of the mini-series, I'm going to use a real-world example to motivate what we mean by an exponential. Now, many students find this topic one of the harder topics in the Higher Mathematics syllabus, and I think there are some technical aspects to this topic, especially with manipulating logarithms. But what I hope to convince you of in this tutorial is that the effort is well worthwhile, because there are so many examples in nature where exponentials naturally arise, and with exponentials and logarithms, these are the mathematical tools that we use to understand those phenomena. So let me start then with a real-world example. Let's consider some bacteria, and for the sake of argument, let's imagine these are so-called E. coli bacteria. If you've ever seen one of these under a microscope, or if you've seen pictures, you'll know that they are sort of rod-shaped cells, and they are approximately 1 micron in length. A micron is a millionth of a meter. And they, if they have sufficient nutrients, grow lengthwise, and then they divide in two to make two new bacteria. So you would have essentially a original bacteria growing, and then after a certain amount of time dividing into two, and then these daughter cells will also grow if there's sufficient nutrients, and after that same amount of time they will also divide into two. And so what you can see here is that we have doublings. We go from 1 to 2, from 2 to 4, and so on. And for the sake of argument, let's say that the time in between doublings is 15 minutes. I think it's a bit longer than that in reality, but not much longer. But this is a convenient time to choose because it fits nicely into 1 hour. And what I want to do is imagine a scenario where we have, at time 0, we have 1 bacteria. Let's say the number of bacteria at time 0 is 1. And then let's trace what happens. So after 15 minutes, this first bacteria has divided into 2. And then after another 15 minutes, so a total of 30 minutes, each of these 2 bacteria will have divided, and we now have 4. Another 15 minutes, each of these 4 divides, we have 8. Another 15 minutes, each of these divides, and we have 16. And this, of course, is now 1 hour. So if you like, you can imagine the scenario of the kitchen that could be cleaner. So the countertop, say, has some food remaining on it overnight, and a single bacteria is taking these nutrients and dividing every 15 minutes. And after 1 hour, we have 16 bacteria. Now let me also just label here the number of time periods. So I want to define one time period to be 15 minutes. That's sort of the doubling time. So that would be an easy way for us to just keep track of this. And for the sake of argument, let me call that n, the number of periods, number of doubling periods. Now, part of my motivation here is to emphasize to you that exponential growth is extraordinarily rapid, and you won't quite appreciate it yet from what we've said, because you might say, well, after an hour there are just 16 bacteria, which is a tiny number. But what we'll see is, as we follow this through, that there will be an explosive growth, and that really is sort of the feature of the exponential function. So let's fast forward 1 whole hour. So now 120 minutes or 2 hours, which would be another 4 of these doubling periods. So we have 8 now in total periods of doubling, and each of these 16 bacteria will have gone through 4 doublings. So we will actually have here 16 times 16 bacteria, which is 256. Let's go forward another hour. So 12 in total doubling periods, 3 hours in total in time. And each of these 256 bacteria will have now gone through 4 doublings. So we have 16 times 256. And can I work out what that is? That's 4 doublings. So that's 512, 1024, 2048, 4096. That's the extent of my knowledge of powers of 2. I'm not going to be able to do any more than that. So let's approximate this. Let's say this is approximately 4,000. Because the numbers are going to get so big, we don't need to worry about every single significant figure from here on. Very good. So after 3 hours then, there are 4,000, roughly, bacteria. This is, of course, assuming that each bacteria has sufficient food. Let's go forward 3 more hours. So let's speed up the film, as it were. So we have 6 hours in total now. This will be 24 doubling periods, and each of these 4,000 bacteria will have gone through 12 doublings, and so we will have 4,000 times 4,000 bacteria, which is 16 times 10 to the 6, using our knowledge of manipulating indices that we have from National 5 Maths. So after 6 hours, 16 million bacteria. Let's go forward another 6 hours. So that will be now 12 hours in total. It will be 48 doubling periods, because there are 4 doubling periods in each hour. And the number of bacteria will be 16 times 10 to the 6, and each of these will have gone through 24 doubling periods. So each of them will have created another 16 times 10 to the 6. And this number is 256 times 10 to the 12, 256 trillion, which is approximately, I'm not even going to worry about the factor of 2 there, roughly speaking, we have 10 to the 14 bacteria now. That starts to be a very seriously big number. 100 trillion, I think that is roughly the same as the number of cells in the human body. And just slightly with tongue-in-cheek, because of course I'm assuming that each bacteria has access to sufficient food to rapidly grow and double. I think by this point the food in the kitchen will have run out, but let's just pretend that the food is available. After another 12 hours, which would be now 24 hours in total, so one day, there will have been 96 doubling periods, and each of these 10 to the 14 bacteria will have gone through 48 doubling periods and made another 10 to the 14. So we have this many bacteria, within a few factors of 2, so roughly 10 to the 28 bacteria. For those of you who study chemistry, you'll know of 10 to the 23 as a very special number. That's 1 mole in chemistry when it's multiplied by 6, Avogadro's constant. So this is roughly speaking 100,000 moles of bacteria. So an extraordinarily large number, and that potentially from one bacterium doubling every 15 minutes, and after a day you have 10 to the 28 bacteria. Just to give you a sense of how large that number is, let's try to get an understanding of what the volume of this colony of bacteria would look like. So 1 micron is a millionth of a meter. In scientific notation, 10 to the minus 6 meters. So you would need to line a million of these in a row to have the length of a meter rule. Now the volume of one bacteria would be this number multiplied by itself 3 times, roughly speaking. Again, we're just trying to get things roughly to, within a factor of 10. So the volume would be roughly 10 to the minus 6 multiplied by itself 3 times. It's sort of not the spherical cow, it's the cubic bacteria approximation that scientists like to do this so they can make quick calculations. But it's only going to be off by maybe a factor of 2 or something, which is not important at this scale. So the volume of a bacterium then roughly 10 to the minus 18 cubic meters. So you would need 10 to the 18 bacteria to fill 1 cubic meter. From this exponential growth, we have 10 to the 28 bacteria. So the volume of bacteria after 1 day of growth is roughly 10 to the 28 bacteria, each of them with a volume of 10 to the minus 18, which gives us 10 to the power of 10 cubic meters. And it makes sense to convert this to kilometers. There are 1,000 meters in a kilometer, so this would be 10 times 1 kilometer squared, because 10 to the 9 cubic meters is 1,000 times 1,000 times 1,000, so that would be a cubic kilometer. So 10 cubic kilometers, which would, if you could imagine that, it's like taking the volume, it's like taking a town and having that town as the base of a cube and going up into the air by, say 2 kilometers. That entire volume filled with bacteria would be the volume of this number of bacteria. They all came from one bacteria in 1 day's growth if the doubling time is 15 minutes. Now, of course, in reality, you would never have that huge number of bacteria in this scenario because obviously they run out of food. And this is what happens in these biological examples of exponential growth, is that the resource that the entities need to double essentially becomes scarce and the growth slows right down. But let's see quickly, what do we mean here then more specifically by exponential growth? And you can see this quite straightforwardly because this n, which represents the number of doubling periods, we can say that the number of bacteria is equal to 2 to the power of n, because 1 is 2 to the power of 0, 2 of course is 2 to the power of 1, 4 is 2 to the power of 2, and so on. So for example, 256 is 2 to the power of 8. So this final number that we came to, crudely speaking, would be 2 to the power of 96. Taking into account that I've ignored some numerical factors here of 2 and such in these final stages. So roughly speaking. And what we would then say is that this 2 to the power of n is an exponential growth where the base of the growth is 2. If these bacteria were objects that, say, created 3 daughters, as it were, there may in fact be microbes. I can imagine in some fungal organisms you might have something like that. So let's just say there's a microbe that creates 3 entities instead of 2 each time. You would go from 1 to 3 to 9 to 27 and so on, and you would have 3 to the power of n. So this number 2 here is what we would refer to as the base of the exponential, in this case equal to 2, and this formula 2 to the power of n we would call an exponential function. And what I've wanted to illustrate here is how extraordinarily rapid that exponential function is. Where do we see this in nature? Well, this kind of unregulated growth. So if there's just endless resource, then you will have exponential growth in the population. You see it in epidemiology, so with the current pandemic, contagious diseases can be spread exponentially in the sense of how many people are infected. If each person infects 2 others, then the number of people infected will grow in this exponential fashion. You can think of forest fires. If a tree is set alight by a lightning strike, and if that tree can set fire to 2 neighbouring trees, and each of those can set fire to 2 trees, then over time you have an exponential spread of that forest fire. You can think in terms of a runaway reaction in a nuclear reactor. So if the control rods don't work properly, each fissioning atom creates an excess of neutrons that then trigger other nuclei to fission, and you have a runaway reaction, again exponential. So the common feature of all of these examples of exponential growth in the world around us is the sense of a frightening rapidity in the growth of whatever the phenomenon is, whether it be bacteria, whether it be a spread of a virus, whether it be a forest fire, whether it be an explosion of some sort. So the exponential function is a highly dynamic, explosive function. It appears in many, many different places in science. And what we'll do in the next tutorial is take this primitive form of the exponential function and we'll make it a bit more formal and mathematical by thinking in terms of a real variable x instead of this integer variable n. And from there on, we'll be able to do some more kind of regular mathematics, thinking about exponential functions and their inverses, which are what we call logarithms. So I hope this has been interesting and useful, and I look forward to seeing you in the next tutorial. Bye for now.